In this video, we're going to learn about single displacement reactions. Single displacement reactions happen when you have an element over here reacting with a compound, so two elements connected together. And when that happens, the single element, so A, kicks out one of the elements from the compound, for example, B, and then B is now alone, and A is with the other element that B was with. So A takes away B's partner and partners up with B's partner, and now B's all alone. So at the end of a single displacement reaction, something is still alone. It's just something different. A started off alone, and B and C were together. Then after the switch happened, B is alone, and A and C are together now. And that's called a single displacement reaction. There are two general types of single displacement reaction that we're going to see. The steps to predicting the products are fairly straightforward. We're going to start off with, first of all, the general process. So whenever you're analyzing a single displacement reaction, you need to analyze if you have a metal-metal switch or a non-metal switch, and those are the two types, and we'll see that in more detail soon. You'll then perform the switch, and you'll determine the new compound that forms using the crisscross method. And then the element that's alone, if it's Hofbrinkel, make sure it has its proper state and subscript. If it's not Hofbrinkel, then it doesn't really need a subscript because it would be a metal, and that doesn't need subscripts usually. So let's do an example over here. The first type of single displacement reaction is when a metal replaces a metal from a compound, or H. We consider, even though H is a non-metal, when H reacts in single displacement, it's almost acting like a metal. Okay, so just understand that for now. We'll see why later on, but just kind of get that idea. So two metals are switching spots. So A is a metal plus BC. In an ionic compound, the metal is always the first one, so B. So A would kick B out, B's alone, and A is now with C. So you can see an actual example here. You have sodium reacting with magnesium chloride. So right away we can tell this is a metal replacing a metal. How do I know that? Well, the metal is the one that starts off alone. So the metal will kick the metal out. And now magnesium is alone and sodium is with chloride. How is this formula determined? It was determined by the crisscross method. So remember, Na plus Cl minus crisscross, and you get NaCl. How about the states? Well, the metals are solid at room temperature, so they'll be solids. And then if this is aqueous, the compound will be aqueous on the other side as well. Okay, there's other reasons for that, but for now, just kind of go with that general pattern trend, and later on we'll learn the reasons. So let's go ahead and try a few practice problems out together. You can try them on your own if you'd like. So pause the video, then check your work, and then give yourself some feedback. So try to make mistakes and see where you will make some common mistakes. And then that way, when you actually get some feedback on it, you can avoid making those mistakes later on. So here we have lithium. It's a metal. It's going to kick the metal out over here. So that means that magnesium will now be alone. It's a metal, so it's solid. Plus the compound that forms between lithium and iodine. Lithium is +1. Iodine is -1. Crisscross, and you get Li. Oh, LiI, sorry. Lithium iodide. Like that. You could balance this as well. Right now it's not balanced, but if you want to balance it, you could put a 2 over here, for example. That'll give you 2 iodides, and a 2 over here, that's 2 lithiums, and then everything else is nice and balanced already. Okay, so next we'll try the potassium reacting with HCl. That's hydrochloric acid. We'll learn how to name acids later on. This is potassium. It's a metal. And we know that this is a case of a metal kicking out a metal, or H, because H will behave the same way. So K kicks H out. And so H will be alone now, but remember that H is Hofbrinkel, so you have to be careful here. This is going to be H2 gas plus the crisscross between K and Cl. And K and Cl is simply K plus 1, Cl minus 1, crisscross it, and you get KCl AQ. You could balance it. You have 2 H's on the right side. So you got 2 H's on the left side, you put a 2 there. But now there's 2 chlorines, so we need 2 here to get 2 chlorines. But now there's 2 potassium, so now we need a 2 here. So we have 2, 2, 1, and 2. And there we have our single displacement. You can try the next one. Very straightforward, similar to what we did earlier. Just be careful with crisscrossing. So pause it, then unpause and check if you're on the right track. So once again, we have a metal that's alone. And so the metal is going to kick out the metal or H, and in this case, it's an H. And as you know, H, when it's written alone, has to be H2 gas because it's half wrinkle, right? And now you're going to form the compound between calcium and fluorine. So Ca plus 2, F minus 1, crisscross it, and you get CaF2. It started off aqueous here, so we'll keep it aqueous here. You can try to balance it. So we can put a 2 here. That's 2 hydrogens, 2 fluorines. Now we're balanced. It just needs 1, 2, 1, and 1. Okay, so that was an example of single displacement reactions occurring. We've actually done a few examples of this. If you remember, we did magnesium in hydrochloric acid, right? That was one of the labs that you had done earlier, and you identified that as a single displacement reaction. So now you're actually able to predict the products. You can go back to that lab and take a look at the equation that you wrote and see if you recognize, first of all, it's single displacement, and see if you could actually have predicted the products yourself without me having to have written them down in there for you now. And remember, we had hydrogen gas that was produced, and that's what made the pop sound, right? There was a little pop sound with our flame test that was made, and that's what indicated hydrogen gas was there. And you can try that out yourself. You can go, if you haven't done the lab, you should make sure that you go and watch the little video link that was posted for that lab so you can see what that lab looks like. All right, next we have a single displacement reaction, a special type where you have a metal reacting with water. And we've actually seen that demo as well. If you don't remember seeing it, you should look it up. Simply write lithium reacting with water on YouTube or go to one of our links and you can see what happens there. So lithium, sodium, potassium, they're all very reactive with water because they're alkali metals. So let's take a look at how to predict the products there. This one requires a little bit of a strategy. I'm going to show you how to do it with lithium and then you can try it with sodium. So you have a metal over here and it's going to kick the H out, okay? But here's the thing, you're not kicking, I guess, both H's out. You have to sort of rewrite this to make sure you only kick one H out at a time. So you're going to have lithium plus, I'm not writing the states for now. This is my work here. Instead of writing H2O, I'm going to write HOH. Because water really is 2 H's and 1 O, and it's an H over here, and then the OH, the hydroxide here. So once you've drawn it like this, you can simply kick the H out. So you'll have H2 gas. And then the last compound will be formed between the metal and hydroxide. So lithium is +1, hydroxide is -1, crisscross, and you get LiOH, and you can put aqueous for this as well. And so what you made here is some hydrogen gas, but also a compound that contains a base. When a compound that contains hydroxide, when a compound contains hydroxide, we call it a base. We'll learn what a base is later on, but for now, just recognize that when you have hydroxide in it, and no H to balance it, because water is not a base. Water, we call it neutral, because there's H and OH, and they kind of cancel each other out. But when you have OH over here, that makes it a base. So when you have metals reacting with water, especially alkali metals, they will produce some hydrogen gas. You'll see some bubbling, and then they'll produce a base as well. And if you remember during the demo, we had put a little chemical in there that changes color if there's a base. And that's what that was. It identified that there was a base there, it turned pink. So it's not balanced. You could always try to balance it after as well, if you'd like. But first I want you to try the sodium plus water, and then you can go back and try to balance if you need to. So pause the video, try it yourself, and then check your work. So here we have sodium plus water. So I'm just going to write it as HOH. And you can kick the H out. So H is now alone, but it's written as H2 because it's off wrinkle. And then we do the crisscross between sodium and hydroxide. So Na plus 1, OH minus 1, crisscross it, and you get NaOH. And you could put AQ. So what you've done there is you've done a single displacement with the alkali metal and water. You produce hydrogen gas and, once again, a base. This isn't balanced. If you want to, you could go back and balance it. You'd have to count your atoms and then try to balance the end result. So on this side, we have 1 lithium, we have 1 O, here we have 2 H's. And it looks like we have 2 H's here, 3 H's actually. So we're not quite balanced just yet. If we put a 2 here, that would be 2 lithiums. And now we have 2 oxygens. So we also have 2 H's here plus just 4 H's. So if we put a 2 here, now it looks like it's balanced. So we have 2 lithiums, 4 H's here total, and then 2 O's like that. And this should balance the same way. So 2, 2, 1, and 2. And there we have balanced these equations. Please make sure you try these out. These are common equations to balance. So after you've predicted, you can try balancing. Don't balance before you're predicting. Predict first. Don't worry if things don't match up with the exact number of atoms, because the subscripts are determined by crisscrossing Hofbrinkel rules. Then at the end, you can go and fix things up with coefficients. So in this video, we saw single displacement reactions. We saw strategies to predict the products. We really just did focus on the first case, which is a metal replaces a metal. In the next video, we're going to take a look at the second case of single displacement, where a non-metal replaces a non-metal. Strategies are very similar, just you have to remember that the non-metal kicks a non-metal out. So that'll be in the next video.